All right, let's go ahead and look at yet another hypothesis test example. Researchers use experiments to compare heavy media multitaskers to light media multitaskers in terms of their cognitive control and ability to process information. So they did a bunch of tests, but this is one of them. When intentionally distracting elements were added to experiments, a sample of 50 heavy media multitaskers averaged 5.056 seconds, standard deviation of 0.125, to process this information, and 50 light media multitaskers averaged 4.979 with a standard deviation of 0.189 seconds. So, can you conclude that heavy media multitaskers take longer to process information than light media multitaskers at a 1% significance level? Let's read this for its keywords here. We have N is 50, or the sample size is 50, and X bar is 5.056, S is 0.025. Well, that's great, but we have another N, which is 50 here. So we'll call that N2, and we'll call the other ones N1. We have another sample mean, and we have another standard deviation. So I'm labeling all that as the second sample. There are two means here. We're comparing two means. The first is there is no difference, and the second, the alternative hypothesis is there is a difference. It takes longer when you have a heavy media multitasker. So this is a t-test because we're not been given a sigma or the standard deviation for the populations. Therefore, we're going to set up our t-curve. We're going to do, again, one standard deviation above and below the mean. The mean is 0. We're assuming the null is true, which is that the two means are not different, or the difference is 0. Okay, the standard deviation has the following formula, and I'm going to go ahead and plug in our standard deviations for each one to get my standard error for this, which is 0.032. So that means we would expect approximately a 0.03 second. 68% of our samples are going to have about a 0.03 second difference between the heavy and the light medium multitaskers. All right, so what do we have? We actually have the difference between these was more than 0.03 seconds. It was 0.077 seconds. So that, again, is out in the right tail. I'm going to calculate my test statistic with this formula. Well, I know that I'm going to assume the null is true, which means that the two population means are not different, and I plug in the rest of my data to get 2.41. That's my test statistic, my t statistic, and then I want to find my critical values. My critical values come from alpha, and that it's a right-tailed test. That means I have 99% area to the right, area to the left, and 1% to the right. My degrees of freedom here, I'm going to use the smaller degrees of freedom from the two. So N1 minus 1 is 49, N2 minus 1 is 49. I'm just going to have to use 49. My critical value is approximately 2.40. That's just using sort of an approximation with that degrees of freedom. Okay, so I reject the null. In fact, the critical value, the test statistic, sits in the critical region. Therefore, there is sufficient evidence to show that heavy media multitaskers take longer than light media multitaskers. So that's great. We're done. We've rejected the null and showed that one group takes longer, but let's look at it in the p-value method. We want to find the area. Let's see, it's a right-tailed test, so it's the area, 1 times the area to the right of 2.41. I could just use a t calculator for this and get the area as approximately 0.00987. This is less than alpha, so I reject the null. A better way to do this is a 2-sample t-test, and I plug in my mean, standard deviation, and sample size for both samples. This is a right-tailed test. I click this as not pooled standard deviation, and then this is not a pooled test, excuse me. The test statistic is 2.40. That's close, a little due to rounding, not the 2.41. The p-value is 0.009. I reject the null because this is less than 1%. It's not much less than 1%, but it is, in fact, less than 1%. Therefore, I reject the null.